is on the core Chapel developer team here at HPE. And John is going to give an overview of the Chapel runtime for us today.
All right, thank you, Michelle. So yes, I'm going to give an overview of the Chapel runtime. As Michelle mentioned, my name is John Hartman. I've been on the team, I think, about 3.5 years, and I work pretty much exclusively on the runtime for the Chapel programming language. So let's just jump right in here. So, well, first of all, I only have 45 minutes, so I'm going to give an overview, kind of a high-level overview, and delve into a few things. But if there are questions people have and want to go into more detail on things, I can certainly do that some other time. So the runtime is quite a large piece of code that supports a running Chapel program. Structurally, it's organized in what are called layers, although as we're going to see, there's a lot of interdependencies, so it's not possible to layer these things in a strict ordering. It's all written in C, and it breaks down into these different components that I have here. Can you see my cursor, or do I need to do something to make that happen?
I think we see, can you move it around? Yeah, we see it.
Okay, good.
Yep.
So I'll just kind of keep a track of where I am. So the major components of the runtime are dealing with the various resources of the computers on which the locales are running, such as the memory, dealing with the computational resources. A large chunk of it is dealing with communication in a multi-locale setting. We also have support for GPUs, local storage, or well, any type of storage. And then something that's kind of somewhat related to the runtime are the launchers. So I want to talk about those. So these things in bold here, memory, computation, communication, and launchers, are things that I plan on talking about today. And the other things I'm not necessarily going to cover at all. So let's just jump right in. So the first thing I want to talk about, platforms that we support. What makes the runtime kind of challenging is that there's a wide range of platforms that Chapel can run on, all the way from the high-performance supercomputers like the HPE Cray EX series of machines, the older Cray XC. I won't read all of these, but you can see that there's a wide variety all the way down to the Mac on which I'm giving this presentation. We can also run on sort of generic clusters of machines that have workload managers such as Slurm and PBS, So there's kind of a wide range of machines and technologies and capacities that we have to run on it. So that's part of what makes the runtime somewhat complicated. In terms of how the runtime is constructed, if you go look at the Chapel source code, it's basically all into the runtime directory. Since we support this huge variety of platforms, we don't compile everything all at once. Instead, there's a bunch of variables that start with CHPL_ environment variables that control how the runtime is built. So you can pick and choose what you need for your particular platform. So obviously, if I'm compiling the runtime for my Mac, I'm going to leave out a lot of the HPC related stuff. These variables are used when you build the runtime, and it ultimately produces a static library called libchapel.a. And that's linked against the executable that's produced by the compiler from your Chapel code to produce a running executable that you can run on the machine. The way the build system works for the runtime, you can support different instances of libchapel.a for different values of these Chapel_ variables. So for example, I can build the runtime with chapelcom equals none if I don't want to support multi-locales, and I can also build it with chapelcom equals, let's say, gasnet if I want to run on an InfiniBand machine. And that'll result in two different libchapel.a's. And here's an example of kind of the build path. So we have this fairly long, deep build path with libchapel at the end of it, and encoding all of the different values of these environment variables along the way. So for example, here we can see com is OFI with debugging turned on and so on. So you don't need to have different directories to support different builds of Chapel. So you can have one directory and build it for your EX, and another, and in the same directory, build it for your Mac. So any variable that begins with like Chapel_ like this and doesn't have an RT, I guess I should have said that, is used to control the build. And it's also used to control when you're compiling. So if you do have it built for your Mac in an EX. When you actually compile your Chapel program using the Chapel compiler, you need to have the various environment variables set the way you want to choose the way you want your program to be compiled. So these really aren't used at runtime. They're used at the time that runtime is built and the time your program is compiled. And as I mentioned, that we currently do static linking. So we'll statically link this library against the code that's generated by the Chapel compiler to produce the executable, such as the hello executable. And as I mentioned, the proper libchapel.a that you get linked against is selected by these chapel underscore variables. And feel free to go ahead and interrupt me at any time if you want. You shouldn't throw me off too much. So that's kind of how this works. We don't build everything all at once because it takes a long time, and also your executables will be quite large, and so they get tailored for the particular platform on which you're running using these various chapel underscore variables. So that's mechanically how it works. Now we'll jump into the different aspects of the resources that it's managing and how it does that. And sort of the first thing I want to talk about is how we manage the memory of the computer. So the locales are running on particular, I'll probably use the word locale and node a computer interchangeably, but I'll try not to. I'll try to be specific about what's going on here. So if we think about a locale running on a computer, the runtime is responsible for managing the memory that's used by that locale. So as you're running Chapel tasks and they require memory, or you're allocating arrays or things like that, the Chapel runtime is responsible for managing the memory. And then also the runtime itself allocates memory internally for its functions, so it has to manage all of that. Now, right off the bat, we're going to see that these things can't be organized into layers because the memory interacts with the networking layer, so to speak, because the tasks heap and stack. So as we're running Chapel tasks, in general, those have to be accessible to the network when you're running in a multi-locale program. And I'll discuss that more when I get to talking about the network layer. But there are hooks in the memory management to deal with the network properly. So the network fabric needs access to the memory. We have to register them with the network fabric. And then to make things even more confusing, we have different COM layers for different network fabrics. And so some of them require things to be allocated in a particular way than others do. So there's a fair amount of complication associated with the interaction with the network layer. Right now, for our memory allocator, we're using something called JE-malloc. This is our default allocator. And it works quite well. It's very fast in terms of allocating and freeing memory, although we've recently discovered it's not so great dealing with fragmentation. And as you can imagine with memory allocation, in general, it's going to be a trade-off between allocating and freeing things quickly and handling fragmentation well. So we're currently looking at some other memory allocators. MI-malloc is the front runner right at the moment. But currently we build using JE-malloc as kind of our default allocator. And then underneath the covers of all of this, we do have to be aware that our locale is running in virtual memory and dealing with virtual addresses. And then down at the bottom, we have physical pages of the physical machine. And those are the things that the network interface is dealing with. And so that's going to affect us in some ways as well. So to a certain extent, we're going to rely on what the operating system does in terms of mapping virtual pages to virtual pages to physical pages, because we can't directly control that. So there's not a lot to say about the memory. It basically kind of implements malloc and free and does that efficiently and has hooks into the network system to make the memory accessible from other machines. Like I said, I'll discuss that more in a minute. What I want a little bit more complicated, I would say, or involved, is managing computation. So if we think about a modern computer, it's got multiple cores per CPU. It may even have multiple CPUs per machine. And so that's what we've got going on at the hardware level. And then at the level of the Chapel program, we have Chapel tasks, things that are created by begin statements or coveralls or things like that. And so we have to map the Chapel tasks that are being created down to the low-level machine, the cores and things like that. To do that, we're using a lightweight user-level thread package from Sandia. called QThreads. And it's lightweight and user level in the sense that it's all implemented as a library that gets linked in with your application. So we can create QThreads, at user level without involving the operating system at all. And so QThreads' claim to fame is that it's fast, it's lightweight, and it can support a large number of threads, of QThreads. These QThreads are run to completion. When you create one and start running it, it runs until it's done or it yields. It doesn't do any sort of time slicing or interrupting, threads as they're running. As I mentioned, we're mapping Chapel tasks onto QThreads. So when you have, for example, a begin statement, we're going to create a QThread to run that Chapel task. There's a couple of, the QThreads package is quite complicated and supports a variety of different abstractions and a variety of different scheduling policies for where QThreads should run, on which core should a QThread run, and things like that. We're using it in fairly straightforward mode where QThreads has the abstraction of a shepherd. A shepherd is something that runs QThreads. And the way we're doing it, we have one shepherd per pthread. So at the very bottom of the system, we are asking the operating system to create one pthread per core. Then we're binding that pthread to the core. Then we're running a shepherd on that pthread. And then we're running QThreads on top of the shepherds. So it's kind of a stack thing. I didn't draw a picture because I'm terrible at drawing pictures, but it's basically a stacked architecture in the sense that at the very bottom, we have pthreads running on a core, shepherd running on a pthread, QThreads running on a shepherd. All right. The QThreads are assigned to the shepherds in a round robin fashion. So if you do have a bunch of begin statements, it just assigns the QThreads to the shepherds, one after the other. We don't do anything terribly intelligent about that. Well, intelligent is the wrong word. Let's say complicated about that. Yes, Michelle.
So this shepherd term, is that a QThread term, or is that part of the Chapel runtime?
That's a QThread term. So that's an abstraction that they have, and they can allow, I believe they can allow multiple shepherds per core, for example. So they just have and they also have workers, which I didn't even mention because I don't exactly know what benefit they give you. But yeah, that's
okay. And so is shepherd like a queue essentially?
Yeah, essentially.
Okay, got it. Right,
and it just runs things out of the queue, one after the other, and it runs them till they complete or they yield, and then it runs the next one.
Okay.
So great. We're doing, I'm sorry, Michael.
Oh, just real quick, I wanted to say we're not doing work stealing now, but we would like to do work stealing for tasks that haven't started yet. So if anyone listening to this thinks, wow, that's something I want to help with, get in touch about that.
Yes, absolutely. So currently we're assigning them in round robin and they're never reassigned. As Michael said, there's no work stealing. For various reasons, the interaction between the computation layer and the network layer, we can't do real work stealing, but we could reassign, let's say reassign QThread to a different shepherd before it starts running. Once it starts running, we need it to be fixed. So this is important to the communication layer. So the bottom line here is we will create a task on a QThread and pin it to a core, and it will stay on that core until it completes. Won't move around. And then let's give an example. There's a lot of different interfaces to the runtime, but for example, there's a Chapel task, add task that gets called when you create a new task. Well, there's different varieties, but yeah, that's generally what happens. So I have an example here of a little program I wrote. You have to forgive me, I'm not a great Chapel programmer, but here we have an array of integers, of 10 integers. And the important part here is I'm doing a code for all the elements in A, just add 42 to them. And I think they all start off at 0, or they do all start off at 0. So this will set all the elements of the array to 42. So obviously, you'd probably just want to do capital A equals 42, but I wanted to show you what's going on in this particular construct. So when the compiler hits this code here, this code for all, So the code for all is going to execute each of the iterations of the loop in parallel. And so what's going to happen is the compiler is going to change this body into a function. So it's going to compile it into a function, with a particular name. And then it's going to create a task, a queue thread, for each iteration of the loop. So it's going to go through and call that function. First of all, create the queue thread for each iteration of the loop, in this case 10. And then it's going to have those queue threads start running the function that represents this body of the loop. And they're each going to be passed parameters that indicate like which iteration you're doing. All right. And so when we hit this loop, we're going to fire off a whole bunch of queue threads, and it's going to go through the process I just described. And since it's going to be done in a round robin fashion, so the first iteration is going to be on core 0, let's say, for the sake of argument, and then 1, 2, 3, 4, and so on. And so ideally, we're going to have, if we have enough cores, we're going to have every single iteration of this loop running on a different core. So right off the bat, you might be wondering, well, what if this array is really huge? I just have 10, but what if it's an array of 10 million? Do I really want to create 10 million queue threads? So while queue threads purports to be able to support a large number of threads, maybe that doesn't work so well when the array is really large. It's probably not a great way to program it. But in that case, you'd want to use the for all construct rather than co for all. And the for all construct has some mechanisms in it to limit the concurrency at any point in time. So it's going to limit the number of queue threads that are created to prevent you from just creating millions and millions of queue threads, because as you can imagine, each queue thread does consume a little bit of memory. And so with enough of them, you're going to run out of memory. Each iteration of this loop will run on a core until it completes. And then down here, the main, I have just this, printing out the array here. So the main task is going to wait until all of these iterations are complete before it continues on, and then prints out the array to standard out. So that's basically what happens there. So we're constantly creating and destroying queue threads, because we're going to create them for this to run each iteration of this loop, and then when it's done, we're going to destroy them. So it's very important that the threads library be very fast in terms of creating and destroying threads. So that's it on computation. Unless there are any more questions, I'm going to move on to the communication, because that's actually where a lot of the complexity lies, or at least recently, that's where I've been spending a lot of my time. So in the multi-locale case, the locales have to coordinate amongst each other, and they have to communicate and synchronize and those sorts of things. And we have to support a wide variety of things in addition to just sort of Ethernet. We tend to focus on kind of the HPC network fabric, such as the InfiniBand, which is widely popular, the Aries, which is the older Cray network fabric offering, and the current Slingshot offering from HPE Cray. These networks tend to be very high bandwidth and low latency compared to sort of the types of networks I have in my house here. And they provide user level access to the NICs. So the application can access the network without going through the operating system. And there's a lot of details to making this work. There's hardware support in the NIC, but of course we have to worry about protection, meaning we don't want applications to get any sort of crosstalk and be able to send messages and receive messages where they shouldn't. And we have to worry about address translation, because as I mentioned previously, the application says everything in terms of virtual addresses, but down at the bottom, the NIC needs to know what the physical addresses are of the memory that it's supposed to access. So there's a fair amount of complexity in both the application and in the NIC software to deal with the address translation. Perhaps the biggest thing that these networks offer is CPU offload. So the NICs are complicated enough that they can do some of the work that would traditionally be done by a CPU in a network environment. So for example, one computer can access the memory of another computer without involving the CPU. The NIC knows how to do that. And it also supports, they tend to support some form of atomics, where, for example, one computer can increment an atomic variable on another computer without involving the CPU of either computer. And so we get CPU offload from doing that. There's a lot of complexity. I could give a whole series of talks about the communication layer and what it deals, how it deals with correctness guarantees. But you can imagine that we need, for a Chapel program to run correctly, we need to have guarantees about the order in which things happen in the network. And that'll happen. So for example, imagine that a locale does writes a remote memory location and then reads it. What guarantee do we have that it's going to read what it just wrote? Will the network guarantee that in some way, or will it require us to do some sort of fences? Different networks have different solutions to these problems. But either option, whether it's ordering guarantees or fences, they can be expensive in terms of complexity and just in terms of the overhead required to implement them, or to execute them, I should say. And then it gets a little bit more complicated with visibility concerns. So going back to my previous example, suppose one locale does a write to a memory location, and then another locale does a read from the same memory location. Under what circumstances are we guaranteed that the second locale will read what the first locale wrote? And the different networks have different ways that, different guarantees that they either do or don't provide on that. And so there's a lot of complexity that surrounds that. And that's kind of beyond the scope of what I want to talk about today, except just to point out that the different networks do it in different ways. And so there's a fair amount of code in the runtime to handle the different ways that we support memory correctness on the different networks. There's sort of two ways the networks get used by Chapel. One is what is messages, which is also known as two-sided communication, in which the locales send messages to each other. And it's called two-sided because it requires both sides to do something. So one side is sending and the other side is receiving. And I guess it's kind of the receiving that's the important point here, which is in order to receive a message, the remote locale has to allocate a buffer and say, hey, I'd like to receive messages into this buffer. So it actually actively has to participate in the communication. So Chapel uses messages, it uses two-sided communication, and it uses it to implement what are called active messages. And so an active message is a message sent from one locale to another that asks the other locale to perform some action, on the first locale's behalf. So the active message in the Chapel implementation contains a function that you'd like the other locale to invoke, and what's called an argument bundle that contains all the arguments for that function that you would like to invoke. And we use this to implement the on statement. So I've got an example of that just on the next slide. But on statements get translated into active messages that get sent across the network to the remote locale, tells it which function to invoke, gives it the arguments to the function. The remote locale has previously allocated a buffer in which to receive these active messages. It's got a handler, which is a P thread that sits there, notices that messages have arrived in the buffer, takes them out of the buffer and does something with them. In the case of what we call fast active messages, it'll invoke that function itself. But as you might realize, while it's doing that function, it's not checking the buffer for additional messages. So we don't really want it to, spend too long doing that function. So there's a fairly constrained set of conditions that allow it to do the fast active message itself. And I guess sort of in general, what it's going to do is create another Chapel task to invoke the function. So it's going to create a task, a queue thread, and tell it to run the function and all of that. And in that ways, it's kind of similar to what was going on inside the code for all loop, where we were creating a queue thread and telling it to execute the body of the loop. Here we're creating a queue thread and telling it to invoke the body of the function that's the on statement. And then this buffer can be, a problem if it's not large, if it's not big enough. You got these messages coming in, you got to handle them right away. And so this is a little bit of a detail, but if you're sending something that has a really large argument bundle, beyond a threshold, we'll actually use a remote and memory access to get that argument bundle. So I'll explain about that in just a minute here. in a couple of slides, but there are some provisions in there. We kind of assume that the messages that are going to the buffer aren't too large, so we can size the buffer properly, so we're not spending too much memory, expending too much memory on the buffer. Michael.
Oh, John, sorry if you already said this, but the queue threads are cooperatively scheduled. They will not yield to each other, and there's
Right.
no action where we will like interrupt them to get fair scheduling or anything like that. Each one just runs until it completes or it yields. And the reason that I'm bringing that up here is that in some cases it can happen that this active message handler goes to start a task and all the cores are already doing queue threads, and so that just sort of gets in queued, and it can kind of get bogged down and blocked up waiting to create those tasks. In some cases, they're doing something small that another a task on a remote locale needs, and it would be better to do those sooner. And in such cases, the current practice is to put a call to current task dot yield execution.
Yeah. Yeah, thank you. Yeah, so there are some complexities there, obviously, with not everybody can run at the same time, and how do we deal with I guess in that case, kind of excess of concurrency. Yeah, so that's how we handle messages. And so there is an extra thread running in the background to pull these messages from the buffer and do something with them. So here's an active message example. I have an on statement. This is kind of an interesting idiom that we use in a lot of our test programs, but on sort of quote unquote the last locale. So this will work no matter how many locales there are. We're just going to print hello world from whatever locale we are. So when the compiler sees this and sees the on statement, what it's going to do is compile the body of the on, this writeLn function, into a function itself, pretty small one in this case. And so when you deploy the program and you're running the program, both the local locale, the locale 0, and then the last locale, all the locales have a copy of this function compiled into them. And they're just identified by number. This might be function number 17. And so what the main task is going to do is going to send an on, the compiler is going to generate the code to send an active message to this last locale saying, hey, invoke function 17, and here's the parameters, here's any arguments in the argument bundle. So for this particular function, I think that this is a global variable, and so it's not necessary to like package up this string and send it across, but you could imagine that maybe it's not, and this is dynamically constructed, but somehow the argument bundle has to indicate, this is the string I want you to print. So that information would be in the argument bundle. And so the main task that invoked the on statement is going to be waiting kind of here for the on statement to complete, because that's the semantics of the on statement. It's synchronous. And so the remote function sets a quote unquote done flag when it's done. So when it's done this writeLn and printed this message, it sets a flag that tells the main task that I'm done. And so the main task is waiting for a flag that indicates that the on statement is completed before it continues execution on down here. Okay, so that's basically how this works. So it's kind of similar in the sense that the body gets compiled into a function. The dissimilarity is we're going to do an active message over to the remote node, in this case the last locale, saying to execute this function. And then I'm not 100% sure. I'm guessing this one would not be a fast active message. And if not, it's just going to create a queue thread to execute this function and go ahead and do it the normal way, like that. Here's a bit more complicated active message example where I've kind of combined the last two examples into one. So we got this array of 10 things for all the locales. So this is another common idiom, co for all loc and locale. So for every single locale, on that locale, I just want to set, I don't really know. I just want to set an array element to some value. All right, so each is going to go through and set a different element of the array. All right, so logically, if we look at logically what's going to happen here, this co for all is going to create a queue thread this is going to be compiled into a body of the code for all loop. It's going to create a queue thread, one for each locale. That queue thread is going to start up on this function. And the first thing it's going to do is going to do an active message. So this is going to be compiled into a separate function, the body of this on statement. And that queue thread is going to do an active message saying to that locale saying, execute this code right here. And then the thread will wait here until this on completes. And then the main thread will wait for all of these threads to complete, and then it'll print out the body of the array, or the contents of the array. Now, as you can imagine, that's logically what happens, but this is an example where things get a little bit more complicated. This is a very common idiom to do something on all the locales in your multi-locale program. And if we do create a queue thread for each iteration of this outer code for all loop, all those queue threads, all they're going to do is do an active message and then wait for it to complete. They don't actually do anything useful at all, so to speak. So in this case, it'll get optimized away. So some combination of the runtime and the compiler recognize that, whoa, we're trying to do something at every single locale. We don't have like a language construct to do that, but we can recognize it from this idiom in the code. And so instead what happens is the main task, we don't create queue threads at all for this code for all loop. Instead, this code for all loop is going to be do a bunch of asynchronous active messages to all of the locales. So it's actually going to be a for loop. It's going to go through and do an active message to every single locale in locales saying execute this function. But they're going to be done asynchronously, meaning just fire them off one after the other. Don't wait for them to complete so they're all running at the same time. And then what we're going to do down here, instead of having a done flag, these are going to decrement an atomic counter as they complete. And down here, we're going to wait for that counter to drop to 0. So they're going to just fire them off asynchronously as fast as we can. They're going to run in parallel, ideally, especially if there's a long enough body. Then they're going to decrement an atomic counter. We'll see an example of that in just a minute. I'm looking at the time. And then it's going to wait for the counter to drop to 0. The main task is at this point, before it continues on, it prints out the contents of this array. So this is an example of the optimizations that go on. But, the runtime has to support these asynchronous active messages and the atomic counter to wait for them to all complete. The compiler has to recognize what's going on here and invoke this special optimized version of this. And this does lead to, worthwhile performance improvements from doing that. So that's kind of how messages worked. It's so-called two-sided communication. The other things these HPC networks, these network fabrics will do is so-called one-sided communication, where we're not sending messages back and forth. We're just accessing remote memory directly. So one computer can access the memory of another computer without involving the CPUs on the remote computer especially. I tend to refer to these as puts and gets. So one locale can do a put to another locale's memory, just like set something in the memory, and a locale can do a get from another locale's memory, just fetching stuff from the other locale. So that remote locale has no idea what's going on in the sense that the CPU is not involved. It doesn't have to, do a receive for this to happen or anything like that. It just happens. And this second example here goes back to my previous comment about active messages, which is because we're doing receive into buffers, that buffer space is somewhat precious. And so if we're going to receive an argument bundle that's quite large, instead we're going to just tell the remote node, here's the address of the argument bundle, go get it yourself. And so this will allocate space for that bundle and then do the get, and that'll avoid the pressure on the memory buffer for the message receives. So you might be thinking, well, this sounds quite risky, having one locale reading and writing another locale's memory directly. And it is, and so there is protection provided via what's called memory registration. There's other reasons for it, but let's just talk about it in terms of protection. So when your locale starts up, or any program starts up, the CPU, which is executing the code, has to tell the NIC which memory regions can be accessible to remote nodes. So you may not want to make all of your memory accessible via gets and puts, but maybe just some small part of it. All right. So for example, up here with my get and put in the argument bundle, the node that has the argument bundle has to tell the NIC, hey, it's okay if somebody reads this argument bundle for me, if somebody does a get on it. And so that way we can at least limit, which portions of our memory other nodes can mess with and can view. And to make this a little bit more protective, the remote node also must have a key to access the region. So you can't just say, get me this memory. You have to provide a key that gives you access to that. It's basically a capability that says you have the right to access that region. So when you register memory, not only are you telling the NIC, hey, other nodes can access this, but the NIC's going to give you a key that you can give to the other nodes so that the NIC knows that they're allowed to access those regions, right? And so now we have a bit of a problem about how do we pass around these registration keys. It depends on the COM layer, but they either get exchanged during startup or on demand. It varies from COM layer to COM layer. Just pointing out that now we traded one problem for another. We have to pass these keys around in some way. And as I mentioned, without going into details, is the NIC has to do that virtual address translation. So when a locale does a get from another locale's memory, that's going to be in terms of a virtual address. And the NIC has to figure out like which physical address are we talking about here. So the NIC has to do address translation, and we have to give it information to do that. And there's some complexity there I'm skipping over. So here's an RDMA or an RMA example.
Can I ask?
Oh, sorry, yes.
Yeah, this is Kenjo. Thank you. So actually, if it's part of the memory, do you actually register to the NIC? So if I understand, all the heap objects or arrays or whatever can be potentially accessed by remote node. So without any sophisticated analysis, you have to assume that all the objects are potentially accessible from the remote nodes.
That's correct.
Yeah.
That's correct. We don't have any mechanism for one locale to hide things from another locale. That's not strictly true, but like in the case of the Slingshot network, we register a large chunk of memory and then we allocate from within it. And so other nodes can access whatever's in that huge chunk of memory.
So essentially, you make the whole heap accessible from the remote nodes. So
yes,
you register the whole heap.
Yeah. So the heap I'm talking about here is the process. So the locale is running in a process, right? So it's the processes heap that we're making accessible. So all of the memory that we're allocating via JE-malloc, as I mentioned previously, will be accessible to other locales.
Okay, so that doesn't impose any restriction on the usable heap memory for Chapel?
What kind of restriction did you have in mind?
What's the size, heap size?
Well, we're limited by the amount of physical memory in the machine, and of course, some memory gets used by the operating system, and those sorts of things. But yeah, there is going to be an upper limit on how much memory you can register.
Okay, thank you.
Depends. Yeah, it just depends on the platform. So here's my RDMA example. Kind of my previous example. It is my previous example. But what I want to point out here is that inside of this function, it's setting the value of A. Actually changed it, so this is wrong. But it's setting the value of this A. So what's going to happen here is it's going to do a put to put the value into the A array at the right location. So that's what's going to happen inside of this loop. And then I think the last thing that I have time to cover today are network atomics. These are another important feature of the high performance network fabrics, where atomic operations are implemented by the NIC. And so, for example, you can atomically increment a counter without involving the CPU. So if you want to do some distributed computation that requires atomic operations like computing histograms or counters or what have you, you can do that without involving the CPU. The NIC can just do it itself. However, you can't mix processor and network atomics. So if you compile with Chapel COM set to something and you have your Chapel network atomics by default would be set to whatever the network atomics are for that network, then all your atomics are going to end up being network atomics, meaning that all atomic operations are going to end up going through the NIC, even if the atomic operations, the atomic variables on the same node is the core that's trying to do the atomic operations. And that's going to be true no matter how you slice this, that's going to be true for a particular atomic variable, like no matter what programming model you're using, because just the way the hardware works, you can't mix and match processor and network atomics on the same memory location. But the way we do it is we have it set sort of across the board. There are ways around it, but by default, if you're using network atomics, then all your atomic variables are going to be network atomics. If it turns out network atomics aren't supported, like your network doesn't support them, then they're going to be implemented via active messages and processor atomics. So that's going to be hidden behind the scenes. It's going to sort of do an on statement and do a processor atomic to do that. So even if only one atomic operation is unsupported, like you're on a HPC network that doesn't support, or something, I don't know what, then they're all going to be implemented this way. And then furthermore, we're going to use processor atomics if there's only a single locale. So if you run your program with -NL1, we're smart enough to realize that there is no network communication. There's only one locale, and it'll just use processor atomics. And I mentioned that because that is a little bit of a gotcha if you're trying to look at like performance of some algorithm that has atomic operations in it, and you start with your starting point is one locale. You should just be aware that that's using processor atomics, and when you go to two locales, it's going to be using network atomics, and so you could get a performance difference even if the atomic variable and the task that's accessing it is on the same locale. And I'm just showing an example here of an atomic operation where on all the locales we're going to add the ID to an atomic variable. And so that's going to get translated into a call into the runtime. It's going to go down to the network COM layer and actually do a network operation to increment that atomic variable. Those will all get sent to locale 0 where this atomic variable resides, and the NIC on locale 0 will add these values to A. Without involving the local CPU. So I think I'm going to stop there because I'm out of time. The things I didn't get to cover were the launchers, but that's, I can cover that another time. Are there any questions? All right. Well, thanks for your attention. And like I said, I'm more than happy to talk about other aspects of the runtime in more detail in another one of these or offline or however you want to do it. But you should be able to find me, and I'd be happy to answer whatever questions you have. Oh, Bonnie has a question.
Yeah, quick question. I'm just wondering how everything works when you have systems that are failing. So in particular, sometimes nodes on our cluster will just go down and we'll have random failures. What happens? Like for example, in the example you gave where it's waiting for everything to, come back and finish, like what kind of error handling might you need to do to kind of deal with systems that could be a little choppy?
Yeah, we don't really have any fault tolerance in the system, so we're not going to be able to tolerate that kind of failure. Because you imagine you have an array that's distributed across all the locales, and one of the locales goes down. Well, we're not going to be able to recover that. Whether or not, I'm not 100% sure that we're even going to detect a failure and gracefully exit with a useful error message, or whether we're just going to wait. It probably depends on the network fabric as to what happens in that case when you try to contact a node that's not responsive. Let's just say bad things are going to happen.
Yeah, no, that makes sense. But you would just maybe write some like test use cases, make sure everything's kind of up and running, expected results come back, and then, you know, there's only so much you could do. But that makes sense. I was just curious if you had any thoughts about that.
No, I don't. And I mean, obviously, one of the things about like the MapReduce paradigm in the cloud world is that it deals with failures, right? That was their thing, is that we're going to have so many nodes that there's always going to be a failure during a run. But that's not typically things that HPC systems worry about. You know, if there's a node failure, the sysadmins get notified and they reboot the node, and you know, or take
Yeah.
it out of service or whatever they do, so subsequent jobs don't use it.
Good point. Good point. Yep. Makes sense. Thanks.
All right. Anything else? All right. Well, thanks everybody for your attention.
Yeah, thank you, John. I'll go ahead and stop the recording.